Okay, so today we're going to be talking about gas laws. So we talked about gases and their properties on Friday and doing pressure conversions. So let's title this gas laws. That's what we'll be doing today. Okay. And so this first gas law we're going to look at is going to be PV equals nRT, pub nert. And this is our ideal gas law. So let's figure out what all of these letters mean first. Okay, so P, what do we think that means? Any guesses? Pressure, exactly. And B?
Velocity.
I'm thinking volume, because we said we're always going to use three things when we talk about gases: pressure, volume, and let's skip to T. What was the other one?
Temperature.
Temperature. Okay, and N and R, I'll go ahead and tell you those ones. N is going to be your number of moles. And R, it's going to be a constant, and we'll get more to that later when we go more in depth with the ideal gas law. Because today we're just going to use the ideal gas law to help us learn what we need to learn for today. Okay, and so we have 5 gas laws that we're learning today, ideal gas law not included, but we're not really learning it today. And so how we're going to get these gas laws, I'll tell you that. So just kind of bear with me right now. It'll make more sense in a second. So let's write same side. And those are going to go in a line. And we'll see that in just a minute. And let's write opposite side. And those will be in a fraction. Okay, so our first gas law that we're going to learn today is going to be relating pressure and volume, so our P and our V. So are they on the same side or the opposite side? They're on the same side. So we're going to write them in a line. So here's what that means. We're going to write P1, V1 equals P2, V2. Okay, these ones are going to mean that there are initial values. So the beginning values, the starting values. And these 2's are going to be our final values. So if we have initial and a final pressure, does that mean it's changing? Yeah, and same with volume. Our volume is changing. Yes, it's changing, yes. So yes, our pressure and volume are changing. So what about our temperature and our number of moles? What do we think those are doing? So are they doing anything? I don't think so. I think they're going to be constant, and so that's why we don't have them in this equation. So our temperature and our N, our number of moles, are constant. So that's why they're not in this equation. Well, this equation, or gas law rather, it's going to have a name. And its name is Boyle's law. And we boil peas and vegetables. If you want to remember it that way. You boil peas and vegetables. So there's going to be one more thing that we want to take from this law, and that is that the pressure and volume of a gas are going to be inversely related. So if we were to plot our pressure versus volume, since they're inversely related, it's gonna look something like that. So what's another word for inverse? A synonym. So the inverse of something could be like what? The opposite, maybe, right? Yes. Okay. So they're going to be inversely related. So they're going to do opposite things. So if pressure goes up, what does that mean my volume's going to do? It's going to go down. It's going to do the opposite. So if pressure goes down, volume goes up. Okay, so there's one of our laws. And let's figure out what our next one will be. So our next one, we want to make a law with our volume and our temperature. So that means that our pressure and our number of moles are going to be constant. So our volume and temperature, V and T, on the same side or opposite sides? They're on opposite sides. So we're going to write them in a fraction. So here's what that is going to look like. So we are going to have V1 over T1, and that's going to equal V2 over T2. This is going to be Charles' law. Something like that. Okay, so our 1s and our 2s are going to be the same thing. No big deal there. So what's constant during this law? So what did we not include? Because they would have to be constant if we didn't include them. So pressure, we didn't include pressure. And we didn't include our number of moles. So these are going to be constant. Okay, so we want to know if this is what sort of relationship that our temperature and volume are going to have. So Boyle's law was an inverse relationship. So do we think this is going to be inverse?
No.
No? Why not?
Because it's divided.
We're dividing. We're not multiplying anymore. So this is going to be a direct relationship. So the volume and temperature of a gas are directly related. So if we were to plot this with our volume versus temperature, it would look like this. Because in a direct relationship, as our volume increases, what does temperature do? It increases. They're going to do the same thing. So as volume goes down, temperature goes down. Okay, so let's move on to our next law. And we're going to have pressure and temperature with this one. So our pressure and temperature on the same side or opposite sides? They're on opposite sides. So what am I going to write for my law between pressure and temperature?
Pressure, temperature, inverse.
So P1 over what? T1, because we're going to make a fraction. And what is this going to be equal to? P2 over T2. And this is going to be Gay-Lussac's law. Okay. So what are we keeping constant? What stays constant? Volume
Volume,
and the number of moles. So we didn't include them. We only care about the things that are going to be changing. So do we think we have a direct or indirect relationship? Or inverse? Direct or inverse?
Oh, so it's
Same thing.
indirect.
What?
Is it indirect?
I think it's going to be directly, because it looks kind of like Charles' law. We have division in there, we have fractions, so it's going to be directly related. So once again, if we plot our pressure versus temperature, it'll look something like that. And if pressure goes up, what does temperature do? It goes up because they are directly related. So if pressure goes down, what does temperature do? It goes down. Okay. So the next law, we'll start you off with the name, and that's going to be Avogadro's.
I've heard that name before.
Okay, you've heard this name. Where have you heard this name?
I don't remember where.
You don't remember. Does anyone else remember? What else does he has a law, apparently. We're just not learning that. What else does he have? Avogadro's number. And what's Avogadro's number? What's his nickname? The little ugly animal rodent thing. The mole. Yes. Do you remember that?
Hey, isn't it
The
6.02?
mole. Yes, it is. But we're the mole. It's Avogadro's number. Okay. So what do we think that means in Avogadro's law? We're going to have a mole in it, maybe? Moles? I think so. So in Avogadro's law, we're going to be relating our volume to our number of moles. So are they on the same side or opposite sides, our V and N of our ideal gas law? They are on opposite sides. So we're going to have V1 over N1. We're going to turn it into a fraction. Is equal to V2 over N2. So what are we keeping constant here?
Pressure.
Pressure and temperature are going to be constant. And they're going to be directly related. So there's one more thing that we need to know about Avogadro's law. And that's that equal volumes of gases contain equal numbers of moles. So let's write that. Equal volumes of gases contain equal numbers of moles. So if I have a helium balloon, and let's say it has 1 liter of helium in it, and I have a balloon that's filled with chlorine gas, and let's say it has 1 liter of chlorine gas as well, how many moles are they going to have? Is it going to be the same or is it going to be different?
It's gonna be different.
I thought it was the same.
It's going to be the same.
Mass.
It's going to be the same. That's what Avogadro's law just told us.
Oh.
Equal volumes of gases contain equal number of moles. Doesn't matter what kind of gas. It's the same volume. You're going to have the same number of moles.
Oh, wait. I'm thinking mass.
Yep, volume. Same volume, same number of moles. Okay, so that's our Avogadro's law. So we're going to make one more law here. And let's see. So all of our laws, we've had 2 variables in them so far, right? Yep, this one's gonna have 3. And guess which 3? The most popular ones. The ones we said we'd always be talking about. Pressure, volume, and temperature. So we can use our same little trick of the same side in a line, opposite side in a fraction. So let's see. Pressure and volume. Are they on the same side or opposite side? They're on the same side. I feel like there should be more than one person being able to answer that. Yeah. So they're on the same side, so we're going to write them in a line. Now, is temperature on the opposite side of these or the same side?
Opposite.
It's on the opposite side. So what do we have to do?
The equals.
Turn it into a fraction because it's on the opposite side. So we're going to put this over T1. T1's on the opposite side of our PV. And now we're going to make this equal to P2 over T2. So, anyone want to take a gander at the name of this equation? So if you look at Boyle's law, Charles' law, and Gay-Lussac's law, it kind of, what does it do to all of them? It combines them. So this is going to be our combined gas law. Nothing too crazy. Combined gas law. So what's the one thing that we're keeping constant? N is constant. Okay. So these are our 5 laws that we're going to use to help us complete tonight's homework assignment. So I'm going to go ahead and hand that out right now. And then we're going to work through a couple together so we can see what needs to be done. Okay, so let's look at this worksheet. That will be your homework tonight. So the big bold Roman numeral 1, that stuff you did on last night's homework, correct? So I think we're good on that. You can do that on your own. So let's move on to this next section. And they give us instructions. So it tells us first we want to identify each number with a P, a V, or a T. So let's do that first. Let's look at number 1 and do our step number 1. So it tells us the gas in a sealed can is at a pressure of 3 atmospheres. Is that a number? Yes. Hopefully more than one person can answer that 3 atmospheres is a number. So yeah, 3 atmospheres is a number, and we want to label it with a P, a V, or a T. So what is it going to be? A P. Atmosphere is a unit of pressure. And we're going to go ahead and put P1, because it's our first pressure. Okay, so at 25 degrees Celsius, another number. So we're going to stop and label it. Is that a P, a V, or a T? It's a T, and it's going to be our T1. And what did we say on Friday about our temperatures when we work with gases? We make them Kelvin every time. So we don't care about 25 degrees Celsius. We want Kelvin. So how do I get Kelvin from 25 degrees Celsius? I add, what do I add? 273. And what do I get? 298 Kelvin is going to be my T1. Okay, so let's continue. A warning on the can tells the user not to store the can in a place where the temperature will exceed 52 degrees Celsius. What would the gas pressure in the can be at 52 degrees Celsius? So here's my other number. And what is this going to be? T2. And what else do I have to do to this number? Add 273. I don't want to see Celsius. And let's see, what's 273 plus 52? 325 Kelvin. Okay, and what would the gas pressure in the can be? So I want to know, what would the gas pressure in the can be? So what do we think I'm looking for? I think I'm looking for P2. I'm looking for my second pressure number. So let's look at our gas laws that we have. Oh, I don't have any V. I don't care about it. And it's in a can, right? So if it's in a can the whole time, the volume's remaining constant. So if it's constant, it's not going to be in my equation. We only want to know the things that are changing. So what law do I have that relates my pressure and my temperature? Gay-Lussac's law. So we're going to write the law that we're using. And then we're going to write the equation without our numbers in it. So what's that equation? P1 over T1 equals P2 over T2. Awesome. So now we're just going to plug our stuff in. So P1 we said was 3 atmospheres, and I'm going to write my units every single time, and so are you. So write your units every time over T1, which is 298 Kelvin. And this is going to equal P2 over T2. And oh look, it's right there. 325 Kelvin. Okay, so I want to solve for P2. So what do I have to do to solve for P2? Have to cross multiply and divide, right? So if we cross multiply, we're going to get 3 atmospheres times our 325 Kelvin. That's going to be equal to P2 times 298 Kelvin. We can divide by 298 on both sides. And we know that P2 has to be equal to 3 times 325 divided by 298. And that is going to give us 3.27. And what are my units going to be? ATM. How do we know that? Because that's what we put into it, right? We want to know the pressure. So whatever units we put into there are the units we're going to get out. We can't just randomly change our units. They have to agree. We're always going to have Kelvin on both sides. If we're talking about volume, we have to have milliliters on both sides. Pressure, we have to have torr on both sides. Or we have to have, I don't know, PSI on both sides. Your units have to agree, no matter what. And you're always going to get out the units you put in. Always. So, we're going to have 3.27 atmospheres. And we're going to have 3 sig digs. So yeah, 3.27. So, number 2, I would like y'all to do that right now, and we will go over it in a few minutes. Okay, so number 2. So our first step is to read through it, and we want to identify every number that we have. And some of you weren't doing that. I feel like it'll be very helpful. And I swear to you, I still do this when I do these problems. I still label everything. Like, not even kidding. Like, you could go, I could like show you my college test. I label stuff. I list out my givens. So that's what we're going to do. So, a sample of hydrogen exerts a pressure of 0.39 atmospheres. And what did you label this as? P1 at 47 degrees Celsius. So what do we label this as? T1. What else did we do? We change it to Kelvin. So what do we get? 320 Kelvin. So then our gas is heated to 77 degrees Celsius. So our temperature changed. We're going to label it as T2. And we don't want Celsius. So what is it going to be in Kelvin? 350. We just have to add 273. Just 273. And at a constant volume. Do we care about volume? No, it's constant. If it's constant, we don't want it. It's boring. Like, it doesn't matter. We just want the things that are changing. And we want to know, what will its new pressure be? So what do we think we're looking for? P2. We want to know the new pressure, the final pressure, which is P2. Okay, so I have P1s, or I have P's and T's. So what gas law is that? Gay-Lussac's, same one as last time. So I'm going to write that out without my numbers in it. And let's go ahead and plug in what we had. So what's P1? ATM, atmospheres. We'll keep our units. And T1, 320 Kelvin. P2, well, I don't know. So I'm just going to keep it P2. And T2 is 350 Kelvin. So then I solve for P2. So I'm going to multiply and divide by this. So 0.329 times, oh, my calculator's not on. 0.329 times 350 divided by 320. And I get 0.36 ATM. Why is my units in atmospheres? Because that's what I started with. My units are going to stay the same. Okay, so 0.36. We only have 2 sig figs here. So 2 sig figs in our answer. Okay. So units, make sure you're on top of those. They have to be the same. Standard temperature from your notes on Friday. What's our standard temperature?
273.
273 or 0 degrees Celsius. And what about standard pressure? What were those? We had a lot of them. So remember those conversion factors we were using? Those were all of our different pressures at standard pressure. So those are our standard pressures depending on what units you need. So you have 10 minutes to be working on this, and for your homework tonight you need to complete half of this packet. So through number 12, the first 3 pages. So through number 12, if you want to draw a line or write that on the top, through number 12.
There's 6 things? 76.8. 6.8.
Okay, let's look at one more together. So if you want to listen, we can do that. So let's look at number 5. Everyone turn to number 5. So number 5, it's gonna get a little bit trickier. So Ralph, I know. Ralph with a silent 3 in his name has a helium balloon, and it had a volume of 4.88 liters. So what are we going to label this? B1, liters is a volume at 150 kilopascals of pressure. So what are we going to label this? P1. So if the volume is changed, so our volume's changed to 3.15 liters. So what's this going to be? P2. What would the new pressure be? So what are we looking for? We're looking for P2. In atmospheres. This is a different unit, right? We want to know it in atmospheres. And they give it to us in kilopascals. Uh-oh.
This is very not good.
So we have two options. We can change our kilopascals into atmospheres right now. And then our answer will be in atmospheres because that's what we put into our law. Or we can solve for P2 and get our answer in kilopascals and then change that into atmospheres. And that's personally what I like to do better, that second latter option. So what law am I going to use for P1 and V1? Boyle's law. We boil Boyle's law. We boil peas and vegetables. So I'm going to have P1 V1 equals P2 V2. My P1 I said was 150 kilopascals. V1 was 4.88 liters. P2, that's what I'm solving for. And V2 is 3.15 liters. So I'm going to divide by 3.15 on both sides. Oh no. And what should I get for P2? So I shouldn't be the only one doing this. What did you get for P2?
Maybe like 170.
Okay.
What? Oh wow, I'm way off.
So what do we get for P2?
Almost there.
232. Awesome. Thank you. And what's my units? Kilopascals, because that's what I put in. But I want to know it in atmospheres.
Yeah, that's the problem.
So I have to do like what I did on my homework last night and convert to atmospheres. So what's my conversion factor between kilopascals and atmospheres? Yep, 101.325 kilopascals is equal to how many atmospheres? 1.
You're good.
Yep.
2, 3, 2, divide by 1.
And yes, I get 2.3 atmospheres. So units, they have to be the same on both sides. You're going to get out what you put in. I am still talking to you, so you shouldn't really be standing up. So tomorrow, complete through number 12 in your packet. And I hope you all have a great evening.
What was just collected today, like in the last 6 weeks or this 6 weeks?